As we continue through Chapter 10, our next section is on the divergence and integral test. With geometric series and telescoping series, as we saw in the previous chapter, the sequence of partial sums can be found, and then its limit can be evaluated when it exists. Unfortunately, it's difficult or impossible to find an explicit formula for the sequence of partial sums for most infinite series. Therefore, it's difficult to obtain the exact value of most convergence series. In light of those observations, we now shift our focus and we ask a simple yes or no question. Given a specific infinite series, does it converge? If the answer is no, the series diverges and there's no more questions to ask. If the answer is yes, the series converges and it may be possible to estimate its value. One of the simplest and most useful tests determines whether an infinite series diverges. Though our focus in this section and the next session is on a series with positive terms, the divergence test applies to series with arbitrary terms, positive or negative. So the divergence test is kind of curious. It says that if a series converges, the summation of a sub k members converges, then the limit as k goes to infinity, that each member of that partial sum is equal to 0. So a sub infinity is equal to 0, meaning that it's it's leveling out. It's not growing more, and that would be the idea of convergence. Equivalently, if the limit as k goes to infinity of a sub k does not equal 0, then the series diverges. And this is why it's really a divergence test, because what it's saying is if the series converges, then all of the members in the partial sum as we get out to the infinity members or larger members as n goes to infinity, they're going to 0, okay? But you can't use that to conclude that the series converges. By corollary, you can just say as if each of those members does not equal 0, then the series diverges. So this isn't a convergence test. If you find that the members equal 0 as you go to infinity, it's not necessarily a convergence test. So what is this actually saying? Okay. Well, we know with a sequence, we have all these members, a sub 1, a sub 2, all the way out into a sub n or a sub infinity, right? And then we have partial sums. S sub 1 is just equal to that initial member, right? A sub 1, which is the y value. S sub 2 equals S sub 1 plus the difference between those two members, A sub 2, right? Where A sub 1 is the height here, A sub 2 is the difference between, this A sub 2 plus, that's A sub 3, it's too small. This A sub 3 plus A sub 2 is going to equal that partial sum 3. So what the divergence test is saying is if a infinite series or a partial sum converges, if partial sums converge, then each of the individual heights, for example, the new height, A sub 5, etc., they're getting smaller and smaller until they approach 0 or R0, and that's why it's leveling out, right? The height of each difference is becoming less. All right? As the next member has to be 0 because we're adding another member, if you will. So let's look at our first example. This is pretty straightforward. See if you can do this. Remember, we're using the divergence test that says that if the limit as k goes to infinity of a sub k does not equal 0, then the series diverges, okay? So all you're going to be doing is applying the limit as k goes to infinity on all of these formulas and seeing if it goes to 0 or it doesn't, okay? It goes to 0 if the series converges. If it doesn't go to 0, then we know it diverges, okay? So hit pause and try these now. Again, these are pretty straightforward. Here I have infinity over infinity plus 1, right? And so what I can do here is if I can divide the numerator and the denominator by k, I get 1 in the numerator, I get 1 plus 1 over k in the denominator, which goes to 0, and that leaves me with 1 over 1, which equals 1, which doesn't equal 0, okay? Since the terms do not approach 0, the series diverges by the divergence test. Let's try the same thing to b, okay? So notice this is 1 over 2k plus 3k over 2k, or 2 to the negative k plus 3 over 2 to the k. That's just making this into two fractions, what we've done here. Well, this is 1 over 2k, or 1 over 2 to the infinity, or 1 over infinity. So this term goes to 0. 3 halves is greater than 1, so as I raise this to an infinite power, it's getting larger and larger, so it's going to infinity, and infinity plus 0 is infinity. So again, since the limit doesn't equal 0, then we know immediately that this series diverges by the divergency test, okay? If the series converges, then this limit would equal 0, okay? Let's look at C now, okay? When we apply infinity into 1 over k, 1 over infinity is 0, okay? In this case, the terms of the series approach 0, so the divergence test is inconclusive. Remember, the divergence test cannot be used to prove that a series converges. All we know here is this is true if a series converges, but it doesn't conclude, it's not conclusive that the series converges just because this equals 0. So that's why it's called the divergence test, because you can only determine divergency. You cannot determine convergence if a series converges. So even though it looks like this series might converge, we do not know that for sure, so we say that the divergence test is inconclusive. We did the same thing here, and of course if k squared, this is also going to go to 0. As in part C, the test is inconclusive, so we do not know whether it diverges or converges. We now look at an example with a surprising result. Here we have what is known as the harmonic series, which is the summation of 1 over k. So when k equals 1, we get 1 over 1, which is 1. K equals 2, 1/2. K equals 3, 1/3, etc. The question is, does this series converge? Well, this was actually one of the problems in the last example, in example 1. And remember that while all the distance between them does go to 0 as k goes to infinity, all we could tell is that it was inconclusive on whether it diverges or not. Since there's no explicit formula for S sub n, a good idea is to analyze this numerically, okay? So if we look at the first 200 terms for S sub n, it does appear that it's leveling out, and it almost looks like it's maybe leveling between 5 and 6. But if we go further out and take some more measures, in fact at incredibly large values of n, I mean look at the last one is 10 to the 40th power, not even sure where that is, 10 with 1 with 40 zeros, not even sure the name of that number, but you can see that we've gone well beyond 6, etc. So it's still a little bit inconclusive, although it looks like it's getting larger and larger. So something that might help is if you recognize when we look at the original harmonic series, if we made this y equals 1 over x, the same formula, 1 over k, we can see that that this is actually a Riemann sum with left-edged rectangles, where the area of the first rectangle, it's 1 high and they're all 1 unit wide because we're using integers, is 1. And the second area is 1/2, and the third area is 1/3, until we get all the way to this last one, which is 1/n, as we go from 1 to n. And so we can see that this Riemann sum is actually greater than the integral of 1/x dx, or just dx over x, evaluated from 1 to 1/n. Okay, so we can see that the Riemann sum is greater than the integral, which is the area under the curve, for 1/x dx from 1 to n plus 1. Well, note that the integral of 1/x from 1 to n plus 1 equals the natural log of n plus 1. If we apply the limit as n goes to infinity in this, then we're going to see that this integral increases without bound as n increases, right? The natural log of when n is 1, then we get the natural log of 2. When n is 10, the natural log of 11. When n is infinity, we got the natural log of infinity. So it increases without bound. But we know that the Riemann sum is greater than the integral, so we know that the series diverges as well. And so the harmonic series, which is the summation of 1/k, as k goes from 1 to infinity, diverges, even though the terms of the series approach 0. So this is a really good illustration of the idea of the divergence test, that while it can tell you if a series diverges, it cannot tell you that if the individual members of the partial sums are going to a quantity of 0. Okay? The ideas used to demonstrate that the harmonic series diverges, we're going to use those to prove a new and powerful convergence test. We'll see that in 10.5 with some other tests. The fact that infinite series are sums and that integrals are limits of sums suggests a connection between series and integrals. And the integral test exploits this connection. So let's look at the integral test, which is theorem 10.11. Suppose f is a continuous, positive, decreasing function for x greater than or equal to 1, and let a sub k equal f of k for k equals 1, 2, 3, ... Then the summation from k equals 1 to infinity of a sub k and the integral from 1 to infinity of f of x dx either both converge or both diverge. In the case of convergence, the value of the integral, be careful, the value of the integral is not equal to the value of the series. So if we do a proof of this, and your book does a proof on page 675, I'm going to show you an image of that proof, but I'm not going to go through the proof. The proof has to demonstrate two results. If the improper integral from 1 to infinity has a finite value, then the infinite series converges. And if the infinite series converges, then the improper integral has a finite value. Okay? So the way that they do this is that they express the infinite series in two different ways. They start at k equals 2 and go to n, and k equals 1 and go to n minus 1. Okay? And we're demonstrating that with the Riemann sums that we can see are less than the integral area or more than the integral area, depending upon the direction of the concavity of the curve. And what happens here is that it doesn't, what am I trying to say here? This integral test is used to determine whether a series converges or diverges. For this reason, adding or subtracting a few terms in the series, as we see here, or changing the lower limit of the integration to another finite point does not change the outcome of the test. Therefore, the test depends on neither the lower index of the series nor the lower limit of the integral. Okay, so you can walk through again that proof if you want to on 675, but it's showing you here that if we can prove that the integral converges, then by almost like the squeeze theory, that this version of the infinite series converges. And if we can prove that the infinite series converges, this version, then by, again, squeeze, we know that the integral converges. And again, that proof walks through how they define both of these terms and how they're related to each other. So let's look at our next example, example 2, applying the integral test. So let's do this first one together, and then you can try the other two, hitting pause and trying the other two. So first we want to see if we think that, let's use the divergent test, apply the limit as k goes to infinity, and see if a sub k equals 0 or doesn't equal 0, then it's diverging. And we know if that's the case, then they're both diverging anyway. So when k goes to infinity, if we divide all the members by k squared, we get 1 over k in the numerator and 1 plus 1 over k squared. Well, 1 over k in the numerator goes to 0, and 1 plus 1 over k squared, that 1 over k squared goes to 0, so we have 0 over 1, so it equals 0, which indicates that this sum, or that these members are going to 0, which is a possible convergence. Okay? Next, we want to see if the function that we're going to take the integral of, f of x, which is x over x squared plus 1, is a continuous, positive, decreasing function. So we start at k equals 1, and the denominator can never equal 0, first of all, because we have k squared plus 1, so we know it's continuous. As we plug values in here, 1 over 1 squared plus 1 is 1/2, 2 over 2 squared plus 1 is 2/5, 3 over 3 squared plus 1 is 3/10, and so it does appear that these are decreasing. Okay, sometimes it's not easy to figure out if the members are, if the function is actually decreasing, and so what you can do here is take the derivative of the function and then plug in the values and see if the derivative is indeed negative. And so, for example, if we plug 1 in here, we get 1 minus 1 squared, so that's 0. But if it's greater than 1, if it's 2, we get 1 minus 2 squared, which is -3 over a positive number in the denominator. So we start at 0, and then we go up from there, or go down from there. They go 0, negative. So we can see that the derivative is less than 0, which means that it is a decreasing function. When we take the integral of the function, the improper integral from 1 to infinity, remember we've got convergence here, or possible convergence. We don't have a sure sign that it's diverging. So we take the integral because it's inconclusive. Here we get, what they've done here is they've changed the limits, the limits on the integral and applied a limit to the integral. This makes it easier to evaluate, and it's a very common practice, so pay attention to this. So the integral from 1 to infinity is equal to the limit as b goes to infinity of the integral from 1 to b. Okay, so now we can take, here we can see that the integral of x over x squared plus 1 is 1/2 times the natural log of x squared plus 1, evaluated from 1 to b. When we plug this in, this value in, we see that what we actually get is infinity. The natural log of infinity squared plus 1 is infinity, minus the log of 2, which is around a number. So infinity minus 1 is still going to be infinity. So we can see here that the integral diverges, and because the integral diverges, we know the series diverges. Remember, they either both converge or they both diverge. And here we were just checking to see, if we had divergent up here, we don't have to go any further. Okay, so why don't you try B and C. Remember, you're first going to do the divergent test and see if you've got a divergent function. If you've got a sub k equal to 0 as k goes to infinity, then you move on to the integral test, which is making sure you have a positive, continuous, decreasing function, and then applying the limit, the improper integral, Okay? All right, so let's look at B now, and if you haven't hit pause and try it. It's a good idea to try these. Okay? So the integral test can be modified to accommodate initial indices other than k equals 1. The terms of the series decrease for k is greater than or equal to 3. When it's 3, we get 2 times 3 is 6, minus 5 is 1, so square root of 1 is 1, 1 over 1 is 1. If we do 4, 2 times 4 is 8, 8 minus 5 is 3, this 1 over the square root of 3. The square root of 3 is like 1.7, so we have a value less than 1, so we can indeed see that it's going down at this point. We could also take the integral of this, although it's not very fun. Okay? Oh, the last one wasn't fun either, but anyway. So now we apply the limit. So remember, the way that we would take this integral is we would write it as a negative exponent, 2x minus 5 to the power of negative 1/2. And when we do that integral, we would substitute in u equals 2x minus 5 and du equals 2. And that we'd have to add the 2 multiplier inside and a 1/2 on the outside. Okay. So anyway, I'm not going to go through evaluating this integral. You should know how to do that. And the integral of 1 over the square root of 2x minus 5 is equal to simply the square root of 2x minus 5. And when we apply infinity to this, we get 2 times infinity minus 5. The square root of that is infinity, versus minus the lower limit. When we plug in 3, this value is equal to 1. 2 times 3 is 6, minus 5 is 1. The square root of 1 is 1. So we get infinity minus 1, which is infinity. So again, here we have that the integral diverges. We weren't sure because this again equaled 0. So we know the series also diverges. Okay, let's look at our last one here. Again, the first thing we're going to do is apply the divergence test, k as k goes to infinity, and we see we get 1 over infinity, so this goes to 0, which could imply that the series converges. It's just not conclusive. So now we do the integral test. As k equals 0, we get 1/4. As k equals 1, we get 1/5. As k equals 2, we get 1/8. So we can see that it's decreasing and positive for all members, and that the denominator cannot equal 0. There's no value of k that's going to make the denominator equal 0. So we do have a positive, continuous, decreasing function. So now we're ready to take the integral of that and see what happens. Okay, here we've done the same thing of the integral of the integral from 0 to infinity is the same thing as the limit as b goes to infinity of the integral from 0 to b. When we integrate this, we see that we get the result 1/2 inverse tangent of x over 2. when we apply the limit here, we see that this limit value actually goes to a finite value of pi over 4. Because the integral is finite, it converges. The infinite series also converges, but it gets key here that this value of the integral is not necessarily the value of the series. All right. If you need to kind of go through some of this, go back to your Calculus 1 and figure out how to do that integral. That's not a bad time to do that. So we have another long lecture today, and I wanted to give you another break in here. And I thought I'd share another poem by Mary Oliver. This one I really love as well. And this time I thought I'd let you hear it from her own voice. So this is Mary Oliver reciting her poem, Wild Geese.
Wild geese. You do not have to be good. You do not have to walk on your knees for 100 miles through the desert repenting. You only have to let the soft animal of your body love what it loves. Tell me about despair, yours, and I will tell you mine. Meanwhile, the world goes on. Meanwhile, the sun and the clear pebbles of the rain are moving across the landscapes, over the prairies and the deep trees, the mountains and the rivers. Meanwhile, the wild geese, high in the clean blue air, are heading home again. Whoever you are, no matter how lonely, the world offers itself to your imagination, calls to you like the wild geese, harsh and exciting, over and over announcing your place in the family of things.
So again, I hope you like that. I hope you take a moment to absorb that. And also take a break. Get up, walk around, get a drink, stick your head outside, and come back and finish the lecture later. Next, we're going to look at something called the P-series. All P-series can be represented as the infinite sum of the reciprocal powers of the natural numbers. The general formula is the sum of 1 over n to the p for n between 1 and infinity. And you can kind of see that here. So it's the reciprocal powers of the natural numbers. So here we'd have 1 over 1 to the p, 1 over 2 to the p, etc. Okay, natural numbers are the counting numbers. Theorem 1012 is the p-test, talks about convergence of the p-series. And for the p-series that we see defined as 1 over k to the p, this converges for p is greater than 1, converges when p is greater than 1, and diverges for p is less than or equal to 1. So let's look at our next example, example 3. Using the p-series test, we have, excuse me, k to the negative 3, 1 over the 4th root of k cubed, 1 over k minus 1 squared. These are all great examples because they show how you have to be able to manipulate the formula and understand exponents. So go ahead and hit pause and try these. Notice down in the bottom right, I've given you the p-test. Just so, I just told it to you, but here you can refer to it. Converges for p greater than 1. So hit pause and try this. Well, when we look at A, k to the negative 3 is 1 over k to the 3rd power, which would imply that p equals 3. When you look at the model here, 1 over k to the p, k to the negative 3 is 1 over k cubed, so p equals 3, and since p is greater than 1, this infinite series would converge by theorem 1012. Here we have a little one that's maybe more complex, but you should be familiar enough with this by now through algebra trigonometry, Calc 1, and now into Calc 2, how to convert a radical into an exponent. Remember that the root is the denominator, and any power on the entire radicand, what's inside the house, so to speak, is the numerator. So here we have 1 over k to the 3/4. Since 3/4 is less than 1, this diverges. The root is the denominator, the 4 of the power, and what's inside, everything inside is raised to the 3rd power, that's the numerator. Okay? This last one's a really clever one, and it really is one of the challenges of calculus, to be able to manipulate formulas so that you can use tests and theorems, etc. So notice here we have a function in the denominator that's k minus 1 squared, but it starts at 4 and goes up by integer values, to infinity, right? So if we think about what the first value is, if we plug 4 in, we get 4 minus 1, which is 3 squared. So if we start at 3, then we have 1 over k squared all the way to infinity, and we have the same, by changing the indexing, we actually have the same problem, okay? So again, by changing this to k equals 3, we have 1 over k squared. Then we have p equals 2, which is greater than 1, which tells us that this converges, okay? Recall that adding or removing a finite of terms does not affect the convergence of a series. Therefore, the given series converges. Next, we're going to be looking at estimating the value of infinite series. The integral test is powerful in its own right, but it comes with a bonus. It can be used to estimate the value of a convergent series with positive terms. We define the remainder to be the error in approximating a convergent series by the sum of its first n terms. So the idea here is a remainder is the difference between the value of the series, you go from k equals 1 to infinity, so that is the value of the infinite series, minus an approximation, or the sum of the first n terms, okay? And so what's happening here is you're getting a to the n plus 1, a to the n plus 2. You notice you're not starting at a to the n, because you're starting, that first term is going to be subtracted out. Now I just show you this because this is what it's all built on. In your text, in this section, you might want to read through it. It might just confuse you more. I felt like if I tried to explain the proof of estimating series with positive terms, that I was just going to confuse it more for you as well. So I think this is on page 678. You might want to read through the steps. The charts, I think, are really good, and so those can kind of help you visualize what's going on. All right. So let me read this, and then we'll talk about it a little bit and focus on the key parts. Theorem 10.13, estimating series with positive terms. Let f be a continuous positive decreasing function for x greater than or equal to 1, and let a of sub k equal f of k for k equals 1, 2, 3, ... Let s equal the summation from k equals 1 to infinity of a sub k be a convergent series, and let s sub n equal the summation from k equals 1 to n of a sub k, and it be the sum of the first n terms of the series. The remainder, r sub n, which equals s, the sum of the convergent series, minus s sub n, the sum of the first n series, satisfies this relationship. The remainder, r sub n, is less than the integral from n to infinity of f of x dx. Furthermore, the exact value of the series is bounded as follows. L sub n equals s sub n plus the integral from n plus 1 of f of x dx, which is less than the value of the series, the infinite series, which is less than s sub n plus the integral from n to infinity of f of x dx, which equals u sub n. Okay? So again, I think the important thing here is to look at this remainder, which is really trying to get you within. It's kind of similar to the definition of what am I trying to say? The constraint definition that we looked at earlier in limits, the actual definition of a limit, where you have to be within a certain constraint. And now this integral rule helps us figure that out. Okay, I think this will be easier to be understood if we actually do some problems. So let's do some example problems as we end this chapter. So now let's look at an example. Approximating a p-series. How many terms of the convergent p-series, the summation from k equals 1 to infinity of 1 over k squared, must be summed to obtain an approximation that is within 10 to the negative 3 of the exact value of the series? And B, find an approximation to the series using 50 terms of the series. So these are two good problems, and they use different parts of the estimating series 3 theorem 1013. The first part, since we're going to find an approximation within a specific value, then what we're trying to do is find this value of 10 to the negative 3 of the remainder. Remember, the remainder of the series is less than the integral from n to infinity of f of x dx. So we want this remainder to be within 10 to the negative 3, right? So that our answer has to be less than 10 to the negative 3, all right? So we want the remainder to be less than 10 to the negative 3, okay? So if we use this to figure out that remainder, again, we want the remainder to be less than 10 to the negative 3. We can first find a formula for f of x using the given summation, 1 over k squared, right? So what we're going to do is take the integral from n to infinity of 1 over x squared dx, okay? When we do that, I'm not going to go through this integral. You can solve this. It's a simple integral. We get 1 over n. To make sure that the remainder is less than 10 to the negative 3, we're going to set up that equation. 10 to the negative 3 equals 1 over n, or 1 over n is less than 10 to the negative 3. And when you multiply this out, you get that n is greater than 1,000. In other words, we have to sum at least 1,001 terms of the series to be sure that the remainder is less than 10 to the negative 3. Okay? So again, remember n is the number of the terms because it's from n equals 1 to how many, etc. And our remainder is going to be that constraint, if we will, within a certain value of the answer. And this was wanting to be what? 1/1000th of the value. Okay. In our next problem, we want to actually find an approximation for this series within 50 terms. In this case, we're going to use the longer formula where the value of the series is bounded above and below by these two formulas, s to the n, so a partial sum of n terms, plus the integral from n plus 1 to infinity of f of x dx, and it has an upper bound of s to the n plus the integral from n to infinity of f of x. Okay, well, we've already done at least one of those integrals, and we got 1 over n for the left side here, right? Correct? That was for the right side. I don't know why I said left side, sorry. Okay, And that's what these are standing for, upper and lower. This is the lower bound, this is the upper bound, etc. We can figure out S sub 50, right? So we want this to go from k equals 1 to 50 of 1 over k squared. All right, so we need to figure out S of 50. We need to figure out this integral, and we already have this integral as well. All right. So this is what I've already talked about, this part here. We've got to figure out both those parts. When we take the integral on the lower side, we get literally 1 over n plus 1, similar to as we got 1 over n. So the series is bounded between s sub n plus 1 over n plus 1 and s sub n plus 1 over n. We can find, using your calculator, you can do a summation of the first 50 terms, and you get 1.625133, right? And then again, we're going to substitute 50 in for all of the n's. Why are we doing that? Because the problem specifically stated 50 terms. So we have s sub 50 plus 1 over 50 plus 1 is the lower bound, and the upper bound is s of 50 plus 1 over 50. Here's the calculation for s of 50. You should definitely know how to do that on your calculator. You can easily Google that with the TI-84, calculating infinite series values, or partial sums, I should say. Okay, so we get that the value is between 1.644 and 1.645, more digits. Taking the average of these two gives us an approximation of 1.644937. Okay, so I wanted you to see this because they're using different parts of the theorem 1013, estimating p-series, and you need to know these parts, the upper limit, the lower limit, and then of course the remainder and how you can apply them.